Good afternoon. My name is Otto Ballintijn, and I'm here to tell you a little bit about how to use inertial navigation technology or gyro mapping to obtain critical pipeline data, including as-builds, bend radius, inclination assessment, and so forth. Before I go into it, I would like to thank Jonathan and his team for organizing this event yet again. And it's been well organized, and I will be definitely taking part for many years to come. Reduct, a little bit about us. We are a leading developer of inertial navigation-based mapping systems, or gyro mapping systems. And over the past 20 years, we've basically developed solutions for pretty much any underground utility and duct, starting from 30 millimeters upwards. I like to start always with this picture because it kind of sums up what our issues are down under. If we look at the as-builds of all of these utility owners and we lay them on top of each other, I'm sure this is not the picture we get. So there is an issue with legacy data and so forth about the accuracy of underground infrastructure. It's not as bad as this, of course, all the time, but it kind of sums up what we're facing. So with all the sophisticated technologies to present and display and to visualize what's underground, it all comes down to the accuracy of the data that's fed into these systems. So let's talk about that a little bit. Gyro mapping, what is that actually? Well, basically a gyro mapping device, here you see one, is a device that has a sensor unit, and that sensor unit is passed through the pipe, and it basically records its central axis. So the better it is aligned with the orientation of the pipe, the better your result is. So fundamentally, it records the changes in heading, in pitch or inclination, in roll, and lastly, the odometer will tell it what distance is traveled or what speed it's traveling at. And it does this at 100 Hertz or 100 samples per second. So that means if you're traveling at 1 meter per second, you get about a point per centimeter, which is high frequency. And I'll come back to that a little bit later. That's basically what this discussion is about, to help you understand what benefits high frequency actually gives you compared to conventional locating and mapping technologies. So this information is recorded inside the probe, and once it comes out, it's connected to the laptop, uploaded, and then created or merged actually with the entry and exit point coordinates. So we have an exit and an entry point. The tool has passed through the pipe. We don't know how it went from A to B. We just know it went in here and it came out there. But when you take the data from the tool, you tell the software the coordinate that you started at, the coordinate that you ended. It will then calculate this three-dimensional line. It's actually a three-dimensional line, and you see here the depth profile of that particular horizontal drilling in this case. But it gives you an accurate view as to where that pipe is. That's as simple as it operationally is. Now, what is the benefit of using inertial navigation? You basically can use it in any utility. It doesn't really matter as long as it's a duct, it goes from A to B, or even if you have an A point, we have some solutions. But any utility, it will function. Any pipe material, and that's an important one. We have PE or concrete or PVC, but also steel. Because the tool is autonomous, in other words, we don't have any communication with the tool or don't need any communication with the tool as it's traveling. We don't need to send a signal out. So we can be in a cage of Faraday, as they call it in a metal case. So we don't need to be worried that signals get lost. Very important point is, as I mentioned before, we only need the entry and the exit coordinates as references to let's say the real world. We don't need to trace the tool or the probe as it's traveling from A to B. And that's an advantage because, for example, you can go to any depth as long as you know where it goes in and where it comes out. What happens in between doesn't really matter, so any depth is possible. You can use it next to electromagnetic noise generators, as we call them. So it's whether it's a power cable or a train track or anything like that, or steel plating, anything that normally would interfere with the traditional locating technologies, inertial navigation doesn't have that issue. We map at high point frequency, and I try to visualize that a little bit. So traditional methods of locating, you're somewhere between 3 and 10 meters, let's say. You have a point, but because you have such infrequent points, you start to miss things, particularly in smaller ducts. If you have a high frequency mapping technology, you see that that dotted line already follows the contours of that particular pipe much closer. And a little later in this presentation, we will show you the benefits of that. Most importantly, or very important, it's open platform that in our case, which means the output can be directly uploaded into any of the popular GIS platforms or even Excel or anything like that. So we don't have any further conversion requirements to get it from our software into your GIS platform or whatever you're using. And that eliminates human error to a large extent. So what do we use it for? Well, first of all, GIS platform management. It creates an accurate as-built and it's uniform data. But more importantly, it is a perfect technology to verify the contractor's work and be a very key component in the contractor handover management. So if you have a piece of network built by a contractor, it's not very healthy to receive an as-built from the contractor himself because he built it. It's better to have an independent software or technology basically decide whether the contractor's work is up to the specifications in the tender document. So for HDD, that can not only be the as-built, but it also can verify the bend radius of a particular pipe, which is a specification, for example, in pressurized pipes. And in the wastewater segment, we can provide you with a very, very detailed inclination and grade verification. We have a special module for that to tell you whatever your specifications are, how many samples are inside and outside. Like over here, you see that the red ones are outside of the spec and the green ones are inside the spec. And the spec is, user defined. So you decide what your specs are, and then you can immediately see in one chart where it has or has not met your specifications. For the existing infrastructure, it's basically a method to upgrade old analog as-builts. This is particularly true for a number of networks that were built fairly long ago, and pretty much most of the telecom and data ducts that have been put into the ground in the 90s. Very poor mapping was done at that time, and now we are mapping a lot of those infrastructures to understand where they are and to avoid damage when work is going to be done near them. The last one is maintenance planning. Now there's a lot of static maintenance programs whereby utilities say, okay, we will manage or maintain a certain segment of pipe after X years of operation. We will do this, that, and the other. If you map frequently, you can start to see the movement of pipes, if there is any, and then redirect your maintenance to points in the network where you expect failures to be happening sooner rather than later. So that creates a dynamic maintenance element to it, and that reduces unnecessary maintenance. And maintenance cost, as we all know, is a large chunk of a utility's budget for any infrastructure. So a bit more about high frequency data, as I mentioned. So using traditional surveying or locating technologies, it typically yields a coordinate every few meters. In this case, we've said 3 to 5 meters. And the point frequency is not constant. It depends a little bit on the contours of the above ground, how often you can take a point, if there is any blockages to be able to physically walk over the pipe. It is more difficult to get. The ground conditions are sometimes the reason why a regular frequency is not possible. So the surveyor determines the frequency depending on the situation in the field. Using gyro, gyroscopic technology or gyro mapping, you basically log at 100 Hertz. As I said, we don't need to trace from above, so the tool just passes through the pipe and it creates a point pretty much every centimeter. So that's a high frequency, a much higher frequency points. So the best way to show you how that benefits, who could benefit you, is to run you through a couple of case studies. And we have three. We're mapping a bundle of cable ducts prior to dredging a canal. And we're locating, there's a second one is locating a damage in a larger diameter water main. And the third one is assessing the grade of a gravity sewer. So let's jump into the first one. So here we see, this is back in 2013, we see a line that was the line in the GIS platform of the network owner. And there were two manholes, as you see over here. These type of manholes is a data duct, by the way. It's a 40 millimeter ID duct, the standard DN50 size pipe. And there were two manholes, one here and one here. And the line in the GIS was as such, but the owners already knew that was incorrect because they could see when they opened the duct that the pipe was coming in from the south, not from the side. So they knew this line was just a placeholder, but they had no idea how it went from A to B. They had expected something like this, that it was drilled in a, they knew it was horizontal drilling, of course, but it was drilled in a curve so that they could come up underneath the ground and go into the duct. So we went in with a DR2 tool, and what we found was actually that the horizontal drilling went all the way to this parking lot, and then it was just trenched back to the road like that. So this is a huge deviation from the information that was present in the GIS platform. Now you may say, hey, that's funny or whatever, but what's the importance of this all? Well, first of all, there's two things that is important. Number one, it goes underneath private property, which is sometimes a big issue, particularly for the data ducts and other activities. But secondly, today this is a parking lot. Tomorrow it could be a building. And if this asset owner was asked, okay, can you tell me where your network is? And they would give a guesstimate that it was the curve. Then they say, no, we're not in the parking lot. We're somewhere near the canal. Well, let's see. This is 2013. Let's see what happened. So this is the current situation, 2022. And you see they build a building here, and this parking lot has been extended. So for sure, they have been working in and around this infrastructure, which is only less than a meter deep. But at least they could tell the customer or the contractor where their assets were when they were rebuilding this area. And that's the critical thing. You want to reduce the damage to your infrastructure. And hey, I may be in the way, but at least I know where I am, and please don't destroy my infrastructure. So that was an important finding for the short term. The short-term purpose of the measurement was to find the depth here because they were going to dredge the canal. But secondary, this information about a completely different location of the asset helped them 7 years or 8 years later to prevent damage to their network as they were building out that parking lot. The second case that I have is locating potential damage in a large diameter water. This one is a little bit complex, but basically it's back in the Netherlands. There is a huge water main running here. That was known already. There's nothing secret about that. And unfortunately, this satellite picture was taken quite close after we did the job here. Can you still see the area where there was some work done? The challenging thing here was twofold. Number one, the pipe was only had one access point over here. There was no access point over there. This is a horizontal drilling, by the way. And the second one, it's a large diameter pipe, 1.40 meters, I believe it was internal, and it was waterlogged. Now, the issue here was that this dike, this is a dike, so this land is lower than the water. It started to sink over here where you see that repair patch. It started to sink. And the question was, of course, is the pipe underneath causing the dike to sink? And that was the suspicion. It just couldn't be proven because any existing technology, like a camera or something, couldn't go in because of it was waterlogged and it was invisible. Everything, the visibility was very low. So they wanted to, they came to us and said, can you help us out to find out if there is any issue with the pipe anywhere underneath the dike? So we went in and we found a solution. So these are, by the way, the red line is our mapping result. I'll come back to that later. From street view here, you see again that repair patch and the projected line across that. But anyway, we were only interested in the 76 to 90 meter distance from start, just to see what's happening there. Here you have a picture of the access point. In fact, the water level was so high that it actually came out of the pipe. The pipe is open, so you can understand it's not going to be it's not going to be a very clean view inside. And in order to get ourselves past that point, we used an ROV. So we lowered our tool into the pipe. We had a company that runs ROVs. We made a special device here that it could be grabbed by the ROV, and the ROV pushed us basically all the way up to this point. We were sure then we were past the damage, and then it let go the tool, and the tool was pulled back gradually past the point of damage into the front. And then the pullback is actually the recording of the profile of the pipe. Okay, that's how we've done it. It was very creative and in the end successful. So as I said, this is the total depth profile of the 160 meters we ended up measuring. But we are only interested into the 76 to 90 meter from the start area, which is the part that goes under the dike. So let's focus on that. So here we see the profile of that particular section if we use a 3 meter point interval. Yeah, and I said before that's more or less like the locating intervals that you get. And okay, let's be clear. This is 45 centimeters from here to here, and this is 160. This is 16 meters. So it's the depth profile is a little bit stretched out for your benefit. But here, if you look at this, there's nothing spectacular to see. It's very plausible that this is a very intact horizontal drilling. So let's start increasing the point frequency to see if we can find out a little bit more. So if we go to 1 meter interval, now we already start to see some movement in the pipe, which is suspicious. So we see, for example, here a 6 centimeter drop over a 1 meter length. Now we know this is a horizontal drilling, and that is an unlikely steering activity that a horizontal drill string can make. Yet it's not conclusive that 6 centimeters over 1 meter is going to be a cause of damage or a cause of leakage of the pipe. So let's increase the point frequency a bit further to 10 centimeters. Now all of a sudden we see that there is a clear drop here. The tool fell down. It ran off a ledge and started running again. And in fact, a little bit further on the other side of the dike, we see 2 more spots appearing that are clearly not horizontal drilling related bends. So, at 10 centimeters, we clearly see that there is a drop here of a good 6 centimeters over a very, very short distance. If we go even further to a 1 centimeter interval, we see that jump is more articulated. It's more clear that the tool went down and then went on again. And over here, there probably is something similar happening over here, and over here that's suspicious. So there's a bit more detail at 1 centimeter compared to 10 centimeters, but no real new insights. We knew that there were 3 locations that were suspicious. So as a result, a diver went in fact, and went to those points and did find that the pipe was broken in 2 places, They did some temporary repairs and decided in the end that this whole entire horizontal drilling had to be replaced because it wasn't sure that this repair would stop the problem long term. So they decided to install a new horizontal drilling at a later date. So it was a very successful outcome, and it would have never been discovered had we not had the very high frequency mapping. The third case is assessing a grade, the grade of a gravity sewer. So here we have a new gravity sewer development, and it's made up of a number of segments, many different ones. They were all line drillings, and some of them they were not all line drillings. Some of them are actually trenched. In fact, the discussion I'm going to have with you is I think on this section here, which was a trenched section. Now the issue is not so much, you know, this is a very populated area or anything. The issue was the ground condition. It's very, very soft clay. As you can see, the water, you know, the water stays on top of it. It was very, very muddy. And the owner of the pipeline was worried that, okay, as the trench was open, he could see the pipe laying at the right grade. But as they were backfilling it and running over it with heavy machinery, did anything happen to the pipe in terms of grade? So after full completion of the installation, we had just the manholes left. We went in with a probe like that, with a kind of a skateboard setup, and we mapped a number of these segments. I'm just going to discuss one of the segments that we mapped. So here you see the result of the mapping. The blue line, get my mouse. So this blue line here is the depth profile, and okay, it's a high frequency depth profile. It's in fact we're at 10 centimeters per point per sample. So you see every little movement, but you already see that it's far from perfectly straight. Now again, I have to say this entire drop here is 14 centimeters on a 90 meter length. So this graph has been pulled you know, to its maximum view for the benefit of being able to visualize what's happening with this line. Now, if we just used the zero inclination as a demarcation point, we just want to know where is it inclining up or down, then you see that in quite a number of places, everything is red. It's inclining upward, which is bad, and everywhere where it's green, it's inclining downwards, which is good. Now, if we increase or decrease, I would say, the point frequency from 10 centimeters to 1 meter, we still see the fine details lost, but we still see the significant upward inclinations quite well compared to the previous view. Of course, we have less points, but there where it's inclining up, we can still determine that at a 1 meter point, yet the fine details are lost. So if we go to a 3 meter point interval, all of a sudden we see that most of the upward inclinations are lost. There's a severe loss of detail. Only two very small ones left, and it could even be waved away as saying there's no problem. And at 5 meter interval, complete loss of detail. So this is really a very good way of showing you, and let me show you that a little bit faster, what the point frequency can do to helping you understand what is happening in infrastructure. If I was a contractor, I would give a 5 meter point interval. But if I'm an owner, I wouldn't want to have that. So that summarizes the introduction to the inertial navigation technology and the benefit of high frequency points. I hope I've been able to shed a light on the benefits of using inertial navigation and having those points available. Remember that you have to, just don't take the risk. Just get it mapped. And if you get it mapped with as much detail as you can. If you don't need it today, you may need it tomorrow. And it's the easiest time when you build a network to go into a pipe and obtain the data. I thank you very much for your attention, and if there's any questions, please don't hesitate to ask. Thank you very much.
From Amin, who asks, does this system work to identify the communication conduits crossing rivers with fully filled fiber cables?
The simple answer to that is no, meaning that we need open conduit in order to push or pull the tool. Now, in most bundle applications,
Oh, we're having some technical issues there. We lost
can you hear me?
Now we can. There,
okay.
You're back.
Oh, terrific. Sorry, guys. Yeah, a single conduit that's occupied is a lost opportunity for this mapping, meaning that you want to get in there before it's put into service, either with gas, water, telecom, electrical transmitters, etc. So we need an open conduit in order for the tool to traverse back and forth. What I was saying, I think before I got cut off, was in a lot of these applications we've done, there's a duct bank. There's a bundle of conduits, and typically the operator will leave one of those open for future. And we're able to go in and actually map the bundle. So does that answer the question?
I think so. And then you can follow up with another question if that wasn't clear. Oh, Amin says yes, thank you. So I think that did it.
Okay.
Todd, I've got a question. So I'm not very familiar with it. I got to know this technology last year from Otto, discussed it in SUMSF. How far can you push this type of mapping? How far could you let one of those units ride till you had to bring it back, I guess, or get it out?
Yeah, it's a question of logistics, meaning that in a lot of the municipal applications, we're looking from manhole to manhole, and those spacings are, pardon the U.S. unit of measure, but like 1,000 feet, 1,200 feet type reaches. In gas utility, it's 600-700 feet, and those are well within the reach of this system here. It's a matter of having an entry point to insert the tool and an exit point, or in some cases, a locatable point, a waypoint, meaning that we can go single entry, but we do need to know where the tool stopped. So we'll combine that with a GPS with a SOM to locate where the tool stopped, and then we can do that mapping. So I run projects here in the oil and gas business where I'll do up to a mile. And it's some of these drills that they're doing, critical river crossings, drilling underneath all sorts of existing infrastructure. Our daily drill down here is, anywhere from 1,000 feet to up to 5,000 feet. We've done 3 miles. So there's really not a lot of limit to this. It's a matter of being able to insert a tow line, because this is a towed tool, to go back and forth in the pipe or the conduit to produce the mapping results.
Okay, great. And is it mostly being used in oil and gas, or what, is there a sector that's particularly this tool's proving really useful for more than others? Is it
Well, it's
water?
yeah, great question. Our emphasis down here, of course, is the energy industry. However, I've got colleagues all over North America that are mapping municipal systems, so storm, sanitary, water systems. On occasion, and becoming more critical is telecom. So putting in these 1.25 and 2-inch fiber lays, as you guys can appreciate, it's just going in like crazy. So there's a lot of mapping there. Underground, we're finally getting better structured down here and starting to bury critical infrastructure, power lines and so on, with the risk of all of the hurricanes and tornadoes and flooding and so on. So a lot of infrastructure is going underground, which is opening up a lot of need for this type of high accuracy mapping. And if I can underscore the high accuracy part of it, it's Otto was getting into the the minutia of high frequency and looking at potential breaches or movement in the pipe. We're talking about getting down to inches here, where it's competing utilities in a common corridor, and it becomes a risk, a liability, a reliability thing. So it's just such a critical data element in, and as you guys pointed out earlier, in digital twins is having that level of accuracy and confidence in where your utility is.
Fantastic. Well, thank you so much, Todd. We don't have any more Q&A. Is there anything that you wanted to leave us with before we head to the break?
A lot of my work, committee work and development work that I've done is where the specifications and where the best practices kind of fall short is making an accuracy statement, is saying, here's a source of spatial information. Where did it come from? And as you guys know, as GPS has evolved, now we'd like to have that RTK stamp on it or something. Has this utility been precisely gyro mapped? Is it a drill log? At least having those attributes to say, I know pretty well what the accuracy of this positioning or this location information is. So we call it, the second moment is, okay, we got the coordinates, but where did they come from and how accurate are they? So that's pretty critical.
The metadata, the data about the data.
There you go. Thank you. Thank you for
yeah,
for
there's a old GIS specialist in here somewhere still.
Great, good for you. Thanks for highlighting that. But
No
again,
worries.
congratulations on a great program.
Thank you very much. Todd, thanks for joining us from Texas, and a shout out to the university. We love U of C and their geomatics program.
Terrific. Thank you.